In this video series, I will be introducing concepts taught in digital logic design classes. These concepts are very important for electrical and computer engineering majors. Now, I would first like to introduce number systems. Later on in this course and in these video series, we will be learning ways in which to manipulate binary numbers. So it is very important to learn how to represent numbers in different number systems and understand how they are obtained. Now, there are many different kinds of number systems, but the one that is most important to us is the positional number system. If you think about how we actually count in a day-to-day basis, we use 10 different digits, 0 through 9, which is why what we use is called the decimal number system. When we get to number 10, we don't actually have a single digit that represents 10. So instead, we choose to represent it as a 1 followed by a 0. Now, why do we do that? All will be explained when we think about what a positional number system actually is. So I want you to look at this example, 761.23. The subscript here with a 10 denotes what base we're in. Base 10 is what we use on a day-to-day basis. So this number here can be represented as 700 plus 60 plus 1 plus 0.2 plus 0.03. Now, why do we want to do this? Well, if we factor out the 10 in each number, what we obtain is 7 times 10 squared plus 6 times 10 to the power of 1, and so on. What this represents here is that it illustrates that each digit depends on its position relative to the decimal point, which is very important in how we're going to be applying these to different bases. So now that we've already established what base 10 is, that we have 10 different numbers in our system, digits 0 through 9, it's time to take a look at different number bases. So to start, let's take a look at base 2. Base 2 is known as binary, and following the same concept, instead of having 10 different numbers in base 10, base 2 has only 2 different numbers, 0 and 1. So base 2 is referred to as a binary system, and the reason why it is so important is because it is the basic unit of information in computing and electrical communications. In electronics, there are simply 2 states, on or off. Another base that is very important is base 16, known as hexadecimal. In hexadecimal, we have more digits than we're used to, so to represent these digits, we have the numbers 0 to 9, but since we need 16 of them, we use letters A through F to represent the other missing numbers. So in this case, A represents 10, B represents 11, and so on to F equals 15. So an example of what this number can look like is FDE.2 base 16. So now that number systems are introduced, a clearer way of understanding how different bases work is to count in them. So what I have here is a table showing this column showing decimal numbers, and I'm going to be looking at what these numbers are represented as in different bases. So for example, if we're looking at a binary system, we have only digits 0 through 1, right? So to represent the first number, we have 0. The next number would be 1. But the problem is, in binary, we don't have the digit 2. So to represent the next number, we have to move the 1 to the next position, and we have 1, 0. So it seems like this number is 10, but in binary, it actually represents 2. So the next number following would be 1, 1. And again, we don't have any other digits to use. So we have to move the 1 over to the next position and add zeros. So if we follow these rules, we have 1, 0, 1 as 5, 1, 1, 0 as 6, and 1, 1, 1 as 7. Again, we have no more digits to use, so then we go to 1, 0, 0 and 1, 0, 0, 1. 1, 0, 0, 0. So later on, we will be learning how to actually go from binary numbers to decimal numbers, and different bases we can swap in between too. But for now, just understand the concept of going from just counting in different bases. So now let's take a look at the octal system. If you take a look at the octal system, we have 0 through 7 as our normal digits, but since there's no 8 that is represented in octal, since we only have digits 0 through 7, the next number following will be 10, which represents 8. And if you go down the list, we can see that it goes to 17, and since there's no more digits that follow, we have 20 as 16. Now take a look at what's happening in the hexadecimal column. For digits 0 through 9, we have the same numbers, but this time, for digits 10 through 15, we have letters A through F that represents each of those numbers individually. Now that at 15, since there are no more digits that follow F, we represent 16, or the next number, as 10. So hopefully this made it clear on what number systems are and how counting of them actually work. In following videos, we'll be learning about how to go from one base to another and how there are different techniques and methods for those.